Good morning, everyone. It's coming. I see two new faces today. Could you introduce yourself?
Yes, my name is Rene. I'm from Mexico. I'm doing the PhD here in ESP.
Yes, your background is geophysics or oceanography. Good. And you?
And I am Enrico, and I'm doing the PhD at the University of Crise,
Yeah.
in the Earth System Turbulence.
And your background is
Physics.
physics. Good. So I can. So just for you, these series of lectures are dedicated to a special topic in ocean dynamics. Essentially, I try to introduce or describe some processes that are relevant for the global carbon cycle. So, as a truly physical perspective on what are physical perspective on what are the processes that can influence the global carbon cycle. So, I had few basic concept of how the inorganic carbon cycle works and how this is connected to the organic carbon cycle, so the biological part. And then started to describe the major processes that affect both the uptake of CO2 from atmosphere and the release of CO2 atmosphere. The connection between atmosphere and the ocean is bidirectional, two-way. And so far, I described in more detail what are the processes that affect dispersal of the tracers, and you can consider almost all carbon species, chemical species, and carbon form as dissolved or particulate organic matter. So there are two big components. We forget all the complexity of the biochemistry and biology. We just consider the fact that carbon is stored in the ocean in two large pools. And the two pools have quite different properties in terms of dynamics. Part of them, the dissolved part, is passively transported, these are passive tracers. While the particulate one, it could be the fructose of a small organism, or it could be the carcasses, those are heavy or denser than water. Everybody's heavy, but they are denser than water, so they do sink. So we have an additional component in the velocity, in the advective term, which is the sinking velocity. These are more or less the big picture. Now we are discussing, you will see more in the lecture or the recording. Now we are discussing the role of dispersion. So that case circulation has been already discussed, convection has been already discussed, mixed aerodynamics has been discussed during this course, and they have a role, they do have a role. And I'll try to summarize this at the end of the lecture tomorrow. But now we are discussing more about the role of mixing versus steering versus advection. So that the three elements have different properties, and they are of maximum importance if you look at not the global scale vision of the ocean, but the scale of the organisms. The scale of the organisms is small, and they perceive their environment in terms of small scale. However, the small scale are connected to the large scale. We've seen this today by a nonlinear series of processes. So, understanding steering, mixing, and advection is quite important to understand which are the roles, the relative roles in dispersal and sequestering and recirculation of the carbon in the ocean, and in turn exchange with the atmosphere. There are the deterministic way to cast the equation that rules this, advection, diffusion. But between advection and diffusion there is steering. Steering is the way that you have coherent structure present, but still the system or the dye or the passive tracer keep some coherent structure. So you see in a while what I try to explain. It is something in between large-scale advection and molecular mixing. And the deterministic formulation for the fluid dynamics is obviously the Navier-Stokes equation. But somehow, partial differential equation has the big advantage that they are very well known. They are very nicely written down. It's a long story behind this. And the bad news is that few solutions are known for that, especially when you want to go in highly nonlinear fluids, where the advection term is dominant. So, especially in this case, what is known is that the nonlinear term, in case of steering, mixing, and turbulence, has a prominent role. So we cannot disregard it. In large case circulation, geostrophic balance, purely linear, is quite widely accepted to explain 90% of circulation of global ocean. But whenever you go to the smaller scale, this is no longer true. So we have to acknowledge this fact and try to find an alternative way to describe the evolution of the system. And one method which is used for that is the method of moments, that allows to connect the statistic of the gradient with the squares of the passive tracer with its variance, or the evolution, its variance in time. So we can describe or infer the large scale, the integral of the evolution of the variance of our tracers in terms of its gradient squares. And this is an example, which is synthetic examples has been run in silico as a computer program. And as you see here, we have, this is the equation of our moment, calculated in polar coordinates. This is the derivative in time, and this is the derivative according to the angle. These are the initial conditions, so you have something that is organized linearly this way. but the domain is circular, as you see, and the K, so the concept, the rules of the square gradient is 2 orders of magnitude larger than the ocean. So this term is so high because we can obtain mixing in very high, at a higher speed compared to the condition that you can find on the ocean. So this is a conceptual experiment. It's not a realistic one, both in velocity, speed, in velocity, and in the diffusivity coefficient. Another point is, how do you obtain, or do they obtain this nice filamentation? They create a velocity that depends on the square of the radius. So the outer part of the domain has a higher speed. So essentially you get radial shear, velocity shear, in order to create this distortion, which is quite evident as an effect. And you have an effect due to this differential rotation speed on the twisting of the spiral that are created this way. And this is more and more evident up to time step 16, which is the nominal time, and then in at time 32, everything is smoothed out. You see here? So there is an increasing of the internal structure, so increasing of the gradient of our tracer or die here. Then you have mixing. So the transition is not homogeneous. So you can have an initial condition which is linearly stratified, say linear organized here. After one time step, you can see the differential speed have the first effect, then this is more and more evident, but then suddenly from a highly on a situation with a high concentration of thin striation filaments here, you end up in almost fully homogenized step. And how we can interpret it? We can look at the second order, so the variance, let's say, of our tracer field. And this, as I told you, depends, is second moment, it depends of, is calculated by using the method of moments, calculated at second, for the second moment, of the square of the gradients. But what is interesting is that you don't have a continuous transition between filamentation and mixing. You have this initial steering phase and a concentration varies over a relatively large length scale, and the rate of mixing is low. So here you begin to create filaments, but the filaments are large compared to the the whole domain, so the gradient is not too high. But after a certain time step, well, then the rate of diffusion is large enough to balance the rate of thinning of filaments and have stronger mixing, and the differences tend to vanish, to fade out. And the tendency to reach a very low natural background variance for the system, which is not zero. That's quite interesting in the sense that it's true that this cannot predict exactly what happens, but is very good to explain the asymptotic behavior of the system. So we do know that when you have a rotating system, sooner or later the property will mix up, leaving a very low background, let's say, variance that explains non-homogeneity of large-scale pattern that you can find also in the ocean. However, the point is that how realistic is this description in terms of ocean? As I told you, K in the ocean is the order roughly. And if we look at the tracer, in our case, for example, is dissolved inorganic carbon. You may remember what the dissolved inorganic carbon is. It's the sum of all chemical species in which CO2 is present in the ocean. CO2, bicarbonate, carbonate. All these items are summed up in this variable. We assume this as just to make an example and test the appropriateness of this approach in case of large-scale ocean patterns and circulation. So the gradient of DIC rather, is about 0.1 millimole carbon per 10 meter. You see, not that much at global level, because I refer to the IC at surface. So these are roughly the gradient you can find actually in reality. So if you put this inside, the changes in the variance of DIC is equal 6 and so you see this number in order to obtain a homogenization of this term, sorry, there is a minus here, you should have time which is quite long. just to have an idea. 1 year is this 1 year. So imagine to change significantly this value of order, let's say 10 minus 2, 3 minus 3, that could be something realistic for this value. You should have years, even more, to obtain the first evident results. So, most probably, when you look at small scale in the ocean, we can think about this approach is appropriate. But we have to think about a different element that we here has been not yet considered. Here we work with an artificial rotation with a differential value, which is not constant. In reality, in the ocean, when you work at scale larger than 1 day, 1 year is surely larger than 1 day, we have to take into account also rotation. We cannot exclude the Coriolis force, which is apparent force, but it is so important in the ocean that cannot be safely disregarded. At the moment, this statistic approach has nothing to do with rotation. And even if we made all the calculation, rotation is not present here, not directly. There is a common way, maybe you have already seen that, to assess the relevance of the rotation in the ocean or in a fluid. And this is called the Rossby number. The Rossby number is calculated, obviously, is not is a number calculated from scales, not from specific values. It's not a constant, it's something that changes according to the scale of the process you consider and the velocity associated. So, U is the characteristic velocity, and L is the characteristic length scale of phenomena, and F is obviously the Coriolis frequency. And this is a problem. This is the moment in which the physicist plays his role or her role here, because mathematically this has no sense. Which is the characteristic velocity? Which is the characteristic length scale? It's something which, from a mathematical point of view, has no sense. The physicist knows the problem and wants to explore a certain range of scales. And in base of this physical sensibility, feeling, can decide which is the order of magnitude of U, L. Fortunately, F is not a scale. It's a quite precise number that comes from that. This is the rotational angular velocity of the Earth's rotation. And this is, I don't know, latitude or longitude, one of them. So how do you call it? I don't remember. Latitude? Latitude, okay. Okay. Let's give a look for that. U, which is the typical velocity of a current in the ocean, in your opinion? 1 meter per second, good. And L?
1,000 kilometers.
Yes. this is our latitude, obviously. At the equator, how much is the value of f at the equator? 0. So at the equator, the physics is different. So let's keep that a bit aside the equator, so we can define the Rossby radius. In this case, is 1 over as you see, we are just the ordinal magnitude. You cannot be, there's no meaning to be more precise. This is a very fast back of envelope calculation, but whenever you have this number, and whatever is the number that could multiply it, we know that in this case, f is important. F is important. In the previous case, when you have a circle that rotates a certain velocity and the dimension is quite smaller, is the local rotation that matters, not the Earth rotation. So in that case, you can take into account only the rotation of the tank, of the virtual tank that the experiment we showed in the experiment before, and we don't care about the Earth rotation because it takes much more time. Most probably, the time step could be 1 second, 32 seconds, much less than 1 day, which is the typical time scale to be sure that f begins to matter. On the other hand, this is for large case, but look at the small organism that is very effective to capture CO2, like phytoplankton. Phytoplankton has a dimension and the velocity is essentially the sinking velocity. They cannot move. But the sinking velocity for them could be, let's say, 1 meter per day. That means is MF is always in this case Rossby number is what does it mean? This means that in this case, f is not important. We can study the movement of this organism without considering Coriolis, because the scale of the process is much less. Other things matter here. Most probably, I don't want to enter now, but this scale is the viscous scale. Viscosity will play a major role. That's why so small organism that doesn't swim. They could swim, but not swim, because the prominent role of viscosity for that. But the message is, the number in reality changes a lot. everything, when you think about oceanography, think that the Rossby number is this, but this is true for general circulation. When you look at the microscale processes, the Rossby number is much higher. So it's not true that always Rossby number is small. For our purposes, in large scale system, it's true, but sometimes you see that this could happen, that we can well forget as a first step, can forget the Coriolis. This is important. However, the role of rotation in a fluid is not just we have to consider rotation as an element in our equation, but it has a more in-depth effect on structure turbulence. I don't want to enter into detail on what turbulence is, but imagine you have a rotating tank here, you have a laser here, some particles, and you have here camera, which is moves with the same speed of the rotating tank here. This is transparent, so you can see it. And the relevance of using this kind of adimensional numbers like the Rossby is that you are, in theory, sure that all the processes with the same Rossby number are comparable. So the results that can obtain in tank are similar to those that in ocean has the similar scales. And this is the most important, the most relevant effect that has Coriolis on this turbulence that is generated by the grid. You just have a grid that goes up and down in the tank, and this creates a turbulence. So a coherent structure of small scale that are involved in the whole system, and inertially they propagate. They are not actively generated during the rotation. It's just at the beginning. Then the system is left to evolve alone. When rotation is small, you see that the pattern is homogeneously distributed, and there are not specific large-scale structure emerging. On the other hand, when you have high rotation here and the Rossby is small, large coherent structure appears. So, and this is only due to the rotation. This is important, imagine, for the ocean, for the large-scale coherent structure that we'll see in a moment. But this is something that you see on top or in the scale on bottom. But what happened when you do this in 3D? So more or less the example is the same. You have a very, well, primitive way to create turbulence, but effective one, just shaking hand in the tank. This is not rotating, this is rotating. And what is important is you have a mirror here, you see? And an additional die added, which is passive tracer. This doesn't change the behavior of the system. And the most important thing is that you look at this. These are sort of clouds that are stable. Here you have sort of vertical, coherent, strong vertical alignment, and filamentation is quite relevant. So the previous sample is relevant because what you see here is quite similar of we considered in the rotating synthetic channel. So the role of rotation on geophysical fluids, like the ocean, is the fact that you can have very fine striation of a tracer or a dye in the system. This shows that the fluid itself works this way and creates a 2D structure of turbulence. So the effective role of Coriolis is to create to retain the striation as long as possible before diffusion, molecular diffusion take place, and at the same time try to create vertical homogeneity. So from a purely three-dimensional turbulence that you obtain just shaking your hand in the tank, you obtain something which is essentially 2D, which is quite nice on some sense. So having a bi-dimensional of the ocean is a dream because it's quite simple to be studied. You see something at the surface, and you can imagine that in the bottom the thing goes the same way. Unfortunately, this is ideally works this way. In practice, there's no chance to have this idealized situation, even if in some cases the vertical structure of geostrophic turbulence can work quite effectively, and you can have some eddies and vortices that are barotropic up to the bottom, especially in the ocean. And there is an explanation of that. You see, this is so. Maybe you have already heard about this theorem, the Taylor-Proudman theorem. If you have a steady flow and small Rossby number, so it's moving slowly, and there is elevation. These are conditions that not always are met. The governing momentum equation, you already know that, is essentially the geostrophic variance. And obviously the Rossby's number is less than 1, so the two components, I know that you already have heard about that. One is depending on the horizontal pressure gradient along y-axis and inversely proportional to F and the density. The same for the component along the y-axis for the geostrophic velocity Vg, which is again proportional at the gradient along x-axis and inversely proportional to F and rho. To close the equation set, we need also to use the hydrostatic approximation. You maybe know that the pressure gradient depends only on the density and on the gravity. This very small, well, very idealized sets of equations are used often to understand, to explain circulation pattern in the ocean. This very successful to give a qualitative idea of that. But we want to know, use it different way. And you differentiate it with geostrophic invariant spect Z. And so we have the shear, velocity shear along U, X, and Y axis that are again, quite simply, the same term derived by Z in these two cases. But assuming that rho, it doesn't change so much, assuming the rho is constant, then you have something which doesn't depend on lateral gradient. So the gradient of a constant term is 0. This is, you may recognize here something that is quite similar to thermal wind equation. In case no lateral change in density, you take that the velocity shear, vertical shear is 0. What does it mean? It means that the velocity are constant. The horizontal velocity are constant. And if the horizontal velocity are constant, no vertical velocity is allowed because of continuity. So, in an idealized case, geostrophy implies that the structure is purely barotropic, only 2D structure. And whenever the system tends to the geostrophic balance, the adjustment would move the system toward a situation where the shear tends to 0. So, what we saw before is not only matter of turbulence obtained by shaking hands, but also in case you have pressure gradient that in the tank we didn't have, that are responsible for the adjustment for the circulation of the water masses. So this is a stronger, let's say, statement. In that case, we saw that kinematically the turbulence evolved in turn to have large-scale structure when you have a rotation. In this case, the dynamical component, due to the pressure gradient, create something that can explain the previous qualitative system. They are not the same things, obviously, but they, in both cases, you can have one scale compared to the other, a tendency to have two-dimensional processes as a final or asymptotic stable equilibrium system for rotational fluid. But what happened in reality in the ocean? This is not reality, this is simulation. But it's very good to understand since the model is able to capture the large or medium scale feature of the ocean. You can see here is a Gulf Stream. This is Atlantic current coming into the Mediterranean. But the prominent feature here is not the large-scale circulation, are the eddies. So the ocean is an ocean full of eddies. Eddies are coherent structure that are not driven by wind directly, and they are covering ubiquitously all the world ocean. And even marginal seas like Mediterranean are full of such of eddies. As you see, eddies are not steady, are evolve, they also move. So eddies are important from many points of view. I just anticipate they are able to transport, there's an eddy transport connected to the flux due to eddies that should be calculated in addition to the general circulation. We have already heard about the global conveyor belt, which has not eddy, it's just noise encompassing the whole ocean. Here you don't see any straight line, and you see currents here are depicted by a short track of particles. So it's quite an impressive way to visualize the currents. So it's not qualitatively, it's impossible to assess if the velocity here is 10 centimeters, 10 meters. It's not a qualitative way of presenting results. It's qualitative. It's qualitatively good because it shows the fact that you don't have a smooth laminar flow, it has a turbulent flow. And these eddies largely are geostrophic eddies, where the geostrophy plays an important role in balancing the different density gradient present within them. I just anticipate that. So that's why it's so important to study it. And the other point, because it's important to study it, is the fact they are relevant for biology much more than general circulation. Because the scale, the lifetime of organisms is comparable to the lifetime of an eddy, and the spatial scale too. So what an organism perceives in terms of environment is much more connected to the eddy scale than to the global ocean. Global ocean, general circulation, the global overturning takes 1,000 years. Very, very few organisms can live for so long. And generally, our oysters or our kelp or our organisms settled on the seafloor that are not really perceiving this large-scale circulation. So that's why it's so important to look at eddies with a closer look, especially in terms of what they mean for the organism and for the biochemical processes that can influence the carbon cycle. I first introduced eddy characteristics and principles and so on. Then I talk about, probably tomorrow, the impact of the eddies on the biogeochemistry. What is funny is that if you look at the first map, I remember the map of Nansen for the Mediterranean. You look at the Mediterranean, very nicely depicted the current with small arrows, and you don't see any eddy. But the general circulation of the currents of the Mediterranean, so the major currents, are quite nicely identified. So even very primitive techniques and the expertise of fishermen or the sailors and a limited number of observation and very good thinking that was typical of the pioneers of oceanography, they were able to understand quite nicely what is the general circulation. And there were two hypotheses. The ocean interior was quiescent, no current, no life. Until the 19th century, they didn't think that anything living could live beyond 100 meters. Except some whales and so on. And the idea that to have instability to create eddies was not present. So until 60s, eddy was not considered as an important feature. Then you have the first snapshot from satellite. Let's open a totally different view. Satellite oceanography, which is one of the most important branches today to study the ocean, surface ocean, obviously. You can see in that. Open a new, totally new perspective on what is the circulation of the ocean. And the eddies are so vigorous, coherent structure. They are larger, not more than 100 kilometers, but even more, could frequently smaller one. And they last for days, but can last for even more if they don't have any, say, contact with the boundaries or other eddies. And you see a very nice example. You remember fragmentation here. Fragmentation quite nicely observed. This is a chlorophyll, which is a biological tracer on the coast. Don't remember where is it. Probably the west coast of Canada. And you see very nice example of coherent structure here. With spirals that have two different kind of water, one rich of chlorophyll, the other one blue, without. They are intertwined together and are quite. Here, chlorophyll doesn't show exactly the presence of the eddy everywhere, but only where chlorophyll is present. And you see, chlorophyll is mostly present along the coast because of a coastal dwelling. So you have this pattern here, but for sure you have also already here, like this one, but in where the content of the chlorophyll is less, so they are no longer visible. So the message is. You can observe it well using also biological tracer, but the absence of this signature in biological tracer is not automatically does not automatically mean that they are not present, because if you don't have, say, life there, you don't see anything, but you can have an eddy anyway. What is really important is the fact that they are not directly generated by external forces, wind on density gradient. The density gradient play a role in the adjustment, but are not directly generated by that. And this is a interesting feature. The very problem is that when you have large-scale circulation, you have gyres. We are similar to the eddies. You can have heard about the Stallman solution, Monk solution of the wind-driven circulation, large-scale wind-driven circulation. And these are similar to those, but they are directly induced by the Ekman transport. Here, even the structure is not far from that, are smaller, can be treated statistically, they are highly nonlinear, and are evolving space and time. So you statistically know that in some area, an example here, you can have eddies, but it is not true that every time you go there, you can find it. The subtropical gyre is always there, can pulsate, can change a bit, shift, but polar subtropical gyre are always there, are constrained by the forcing and by the topography. Here you don't have any direct constraint by forcing and the topography in the position and the evolution. which are the major feature of the eddies. So, as I already mentioned, the horizontal scale is the order of 10 to 100 kilometers, and the duration can be small, but typically it's the order of months up to years. There are some very nice examples you see later of eddies detaching of the main current where they extract energy, and they live alone as rings and can live for a while in such a way that a specific ecosystem is able to evolve inside, because it's a water parcel which is separated from all the rest of the ocean. And since the time scale is the order of a year, in this case, and the organism can double in one day, you can imagine that you can have some adaptation of the part of the ecosystem to the specific condition created by these rings. It's quite funny, but this is something that happened, for example, in the Gulf Stream. Also, Mediterranean can have, to a small extent, this eddies detaching from African coast and propagating in the northward and westward because of the beta effects, and in getting larger and larger until they crash because they're too large and the strain, the surface is too strong and they decay. What is important in the calculation of the eddy transport in the large-scale current of the world is the order of 30, 40 Sverter. And the eddy transport, because this number couldn't have any effect on or impact on you, but this is more important, or more easier to remember. The eddy transport is equivalent of the amount of ocean water moved by wind or due to the temperature variation. So we cannot forget eddies in terms of average transport. So all the good model, I'm basically a modeler, a good model, when you want to transport also biogeochemical traces, you do have eddy inside, otherwise your transport will be too weak. And we use call mesoscale as the weather of the ocean weather. Essentially, as the same role, but different scales. You know, atmosphere mesoscale is 1,000 kilometers, and the time scale is much faster compared to the ocean because of different density between atmosphere and ocean. But conceptually, the role is the same. But let's give a look on what is the structure in terms of energy of the ocean current. And let's give a look in order to understand if we are able to detect something that can help understand which are the typical scale and evolution of the eddies. And you see, this is a power spectrum density. You know what is a power spectrum? Is that Fourier transform of a time series squared. So essentially proportional to the energy. And these are cycles per hour. The higher number of cycles, the higher the frequency. And these are in terms of the sort of the velocity square divided by cycle per hour is sort of power, is proportional to power. That's why this is called power spectrum. There is a, well, motivation because we use power instead to energy, because when you have the Fourier transform of a non-finite signal, and is not integrable because the integral diverges. So we are forced to use the power, which is the energy per unit time. And this is proportional to that. There is no mass here, but for our purposes, what is important to see how the frequency, the increasing of the frequency has an impact on the power. So the most powerful frequency are those that are dominant in terms of the circulation. These are real data coming from a current meter settled in northern latitude, mid latitude. What you see, the first thing that you see here is the fact that it's not constant. And remember, this is a log diagram. So the changes are quite significant. From here to here, you cannot see, but there are six order of magnitude. And here, from here to here, you can have 5 order of magnitude. You can span a lot of ranges. But you know that the high frequencies is some cycles per hour, sorry. And here you go from 10 to minus 2 to 10 to minus 10 4. And the lowest the frequency, the highest the energy. So it's true that when you look at the general circulation, you have slow variation, large scale pattern. They are by far the more energetic. And this is clear here, you see. However, you see that a quite standard decline of the energy associated with the higher frequency. And you remember this log diagram. The energy decreases exponentially from the lower frequency to the higher one. And in case of temperature, or in case of velocity, as in this case, the final destination of this slope is the fact that you go from large eddy to small eddy, and up to the smallest one, that at the end dissipate kinetic energy in thermal energy. So at the end of the whole process, for what regard the temperature, the velocity, the momentum, the final end is heat. And this is not directly, is not the heat is not directly obtained by large-scale processes, but essentially, but this cascade of eddies from large to small up to the dissipation line that is viscous, the viscous scale, or Kolmogorov scale. However, here we see that you have other energetic parts inside, which are connected to the internal wave. I don't want to touch this point. You can have surface wave, but in a stratified ocean, you can have also an internal waves that are just moving horizon with the same density. Isopycna can move, oscillate in the same way. The only difference is the surface wave has a return force that is gravity, essentially. In the internal, in ocean interior, the return force is the so-called reduced gravity is the difference of the gravity between the two layers. So it's much smaller, and this means that you cannot have fast waves like a surface. In surface, the period is seconds. Here you have cycles per hour, and few cycles per hour is the maximum that you can obtain. You can see here also some spark connected to some tidal component. The M2, the semi-diurnal, is quite evident here. But for the rest is again a cascade of internal wave, broadband covering all the circle. And here you have the inertial wave. You remember that you can have also a wave which the third form is Coriolis, which is triggered by wind, and is also present here. But forget this part, which is high frequency connected to internal waves. But for circulation, you can have a continuous of energy from different frequencies. So the energy, the eddy is not a single dimension. We look at the patterns that are they seem to have always the same dimensions. Not true. And the energy associated to this pattern changes in time because the nonlinear process, the vector term, move energy from large to small scale in a so-called energy cascade. Okay, this to convince you that the eddies cover a broad band in the power spectrum of the current. And however, physical oceanographers like to have simple concept or simple scale to approximate processes. And the previous spectrum is quite complex to be analyzed, and I took a lot of time just to describe it. Sometimes it's much better to have a simple number that can help understand which are the typical scale of the processes. For example, eddies are characterized by baroclinic structure. You cannot have eddies as we know without having a stratification of the ocean. And a measure of the scale, of the mesoscale, so of the geostrophic eddy, is the so-called Rossby radius deformation. Maybe you have already heard about it earlier. And at this scale, the rotation effect becomes as important as buoyancy or gravity. And essentially, this is proportional to the a typical depth scale. Could be the permanent thermocline depth. Inversely proportional to Coriolis term. Again, this is true outside the equator. And then you have the vertical gradient density. So the density structure, vertical structure matter multiplied by the gravity and the average density. This is squared. And there are many interpretations for the Rossby deformation radius. One of it is measure the length scale over which a dense perturbation spread before being arrested by rotation. What does it mean? I thought many times, but why we use this length scale, which is horizontal one, by looking at vertical gradient? It's strange. And this is something that explains me why. Imagine that you have. I'll explain later because I'm a better slide for that. And okay, you can recognize this as the Grundweiser Weser frequency. So it is the typical oscillation of a water parcel that is moved far from its equilibrium as the frequency on which oscillates along is equilibrium point, having sort of continuous stratification characterized by this vertical gradient. Oh, you see here the Rossby radius obviously has some interesting feature. One, varies dramatically with latitude. Near the equator, or obviously is not defined at the equator, but near the equator is larger than 200 kilometers. In the high latitude is less than 10. And this affects the size of the ocean eddy, which are ruled by far and large on that. It's quite frequent to find larger eddies. So the eddy has this as an initial value, and then in time change the vertical structure again, change the Grundweiser frequency, and change also the Rossby radius. So you can have evolution of eddies that somehow reflect these changes. So this is not the Bible, it's just a suggestion of what are the typical scale you can find for mesoscale in the ocean. And looking at this picture is not quite nice, but over mid-latitude, Ri, the Rossby internal radius, increase westward, reflecting the deepening of thermocline. So this is proportional to this h, which is the scale of the permanent thermocline. This is permanent thermocline is oriented this way due to the general circulation, and obviously this means that the larger eddy are on the east coast. And you can see also in the animation, in the video we saw before, that along the western boundary current, the eddies are much larger. But I told you that we don't think the general belief is that the eddies are not generated directly by the external forcing, but which is the origin of the eddy, which is quite a good point. And let's try to have, this is just a suggestion, it's not a full demonstration, it takes more time, but I just give you a hint for that. And the problem is how to release potential energy. So energy is not created. So if you create an eddy that is able to produce more transport than the general circulation, this energy should come out from somewhere. And essentially, you should have some potential energy available in the ocean that can be released. And let's make a first example, the simplest one, most intuitive. You have two layers with different density, and you can move, imagine to move one water parcel characterized by the density rho A to in the same place of rho B, water parcel, that goes down and is just swap place. In case the density of rho the rho A density is smaller than rho B, this is the final state, and it happened naturally because of Archimedes' principle. You have denser, lighter water parcel in a denser medium, and it pops up, and vice versa for that. This is a natural exchange. Conversely, if this is lighter and this is denser, you have to do some work in order to create this displacement. This is quite intuitive and simple. But imagine to have the current moving, as we saw, because of the general circulation. And we saw that the current, the Gulf Stream, for example, but all the western boundary current out this way, start from warmer water, lighter, so low density, and with a high temperature, for example. And they go northward because of the thermal ice circulation. And in this case, if you move northward, or also eastward is the same, because you know we just said that the stratification this way eastward, but the northward is the same. So we have here the temperature is always less than this one, and so you can also think about that the density acts the same way, because at the moment we assume that density depends essentially by the temperature, and this is true because the equation of state for the density is largely dependent on temperature. And on the second and only late and the influence of the salinity is less important. So if you move this way, for example, you have the boundary current that goes this way, you are moving a water parcel toward higher latitude where the density is higher. And then you create here potential energy. You just ramp up. I didn't do it very well, but and put here a water parcel which is lighter in high energy ambient water. So you have this water parcel has some potential energy. Whenever the accumulation of potential energy exceeds a certain threshold, then qualitatively this potential energy is released. You have the so-called instability of the current, and this potential energy accumulated here is released according to a specific trajectory that can be calculated as at half the slope of usually an angle which is half the slope of the isopaque now. So this is in turn to this equilibrium, creating or transforming this potential energy in kinetic energy. This is the source of the energy for the eddy. This is not the whole story. This is one of the process. The other one could be the anomaly of the Hashimoto, for example. There are other sources. The shear of large current that creates so-called barotropic instability. This is called baroclinic stability because we suppose the ocean stratified. So again, you have a water parcel that moves with the current to reach a certain level in which the environment, the ambient water is much denser, the water parcel is lighter and has some potential energy because it's being accumulated by the kinetic energy, and released because the current is no longer stable. You cannot stand there with this potential energy. Potential energy is released in terms of eddy kinetic energy. And this is the last one for today. Yes. Why the eddy has the shape we saw? Because I talk about water parcel or block or mass of water, which is definitely not with a spiral fall. And imagine that you have this pool of water transported here and released without rotation. What happened? But generally, this collapsed and creates an average value in the final state, right? You have just a pool of dense water in or light water in dense water. Vice one of the two is, as they say, it's symmetric, only the rotation change. It's easier to think about dense water, but it could be lighter. When you release a pool of dense water in light water, this goes down. Is opposite it's lighter, goes up. But at the end, the final state is this one. And the movement are, beside turbulence and so on, if they don't mix, for example, they do reach this final state. What happens when you have rotation? Again, rotation has a major role. When you have rotation, there are some fantastic experiments on it. I didn't find the video on YouTube, but if you have a density gradient in a fluid here, and then you go even this way. You have a dense rho1 and rho2, and rho1 is larger than rho2. No rotation means that this goes this way until you reach a stable situation. When you have rotation with the same initial conditions, but the tank rotates, you don't have this, because when you have a density current created by the pressure gradient here, the density current perceives Coriolis force. And Coriolis force, we know that moves this way tangentially. So the current is no longer able to go naturally to reduce, to cancel the density gradient, but creating only stratification, which is the first case. In this case, you have some potential energy here that is released, but at the end, we have final state we no longer is the lowest potential energy state. In this case, rotation just diverts the density current and then create a circular current. It's just trophic adjustment, which is the scale. You can demonstrate this scale of adjustment is the Rossby radius demonstration. That's why Rossby radius scales the dimension of the eddies. This is important to capture. And to me, it's quite impress you to understand that it's not by chance that you have this structure, because only with rotation you can have eddy creates in this way and shaped with this scale. And the higher is the latitude, the more you go northward or southward, the smaller are the eddy, because F is stronger. And the more you go southward, the larger are the eddy. I think my time is over, and I would, if you have, I'll give you the slides, if you have a memory stick.
You can also put it on the computer.
I don't know how. Also with this, because I'm connected here with my one. Untitled before.
That's this.
Come gli altri?
Altre due? Sì. Ah, sì, vero, vero. Mi ho fatto passare prima della ragazza.
Quella precedente. I download also the previous one because there were some typos, and I just check the correct one. Okay.
Se vuole le trasferisco tutte sul computer.
Sì, anche volentieri. Sì. Mm-hmm. Tu avevi già le prime, sì?